There are a few rare reactions where the rate of the reaction does not depend upon reactant concentration. These are referred to as zero-order reactions. And we're now going to extend the concept of integrated rate laws to these zero-order reactions. So it is rare that a reaction is zero order and independent on the concentration of the reactant. So if I'm investigating a reaction trying to identify the reaction order, I normally will check out whether it's zero order last. Normally I'd check first order first, then second order. If none of those align, then I'm going to go and check zero order. So if I have a reaction with one reactant and it is zero order, then the rate of consumption of that reactant will be equal to the rate constant multiplied by the concentration of my reactant raised to the zero power. When you raise something to the power of 0, you just get 1, so the rate will just be equal to K. So I can take those two terms in the middle there that describe the rate of the reaction and apply the rules of integration to them, integrate both sides there, and I come up with the integrated rate law for a zero order process. And what this rate law shows me is if I plot the concentration of my reactant against time, it will have slope equals minus K, and it will have intercept equal my initial concentration, because this is of the form y equals ax plus b, and a in this case is equal to minus k. So for a reaction that is zero order with respect to A, if you plot the concentration against time, you get a straight line. It'll have intercept A0 and slope equals minus k. So it's kind of similar to the first order process, but in the first order process, you're going to be seeing that a plot of log of the concentration against time has a negative slope equals to minus k. Okay. So similarly, we can take the what we did before, you can take the integrated rate law for a zero order process and derive an expression for the half-life. So remembering that after one half-life, the amount of substance it will have is half of the original amount. And so we can go through here, collect the concentration terms on one side. And then if we divide through by minus k, we get our expression for the half-life. So what we see here is that as our reaction progresses, the concentration of A will decrease and the half-life will decrease as well. So what we're seeing is for a zero order process, the half-life gets smaller and smaller as time progresses. So summarizing, for a first order process, the half-life remains constant as the reaction progresses. For a second order process, the half-life gets bigger as the reaction progresses, and for a zero order process, the half-life gets smaller as the reaction progresses. And if you have the right set of data, sometimes you can just look at how the concentration is varying with time and decide without doing any plots whether the reaction is first, second, or zero order. Okay, so putting all of this information together in the one table, we have the rate laws for zero order, first order, and second order processes here at the top. And then underneath that, this is often referred to as the differential rate law, we have what's called the integrated rate law. We then see under here, we've got a list of how you do what we call the straight line test, what you need to plot. So you can do A versus T. If that has a negative slope and is linear, then you know you've got a zero order process. You can plot log of your concentration against T. Again, if that has a negative slope and is linear, then you know you've got a first order process, and you can plot 1 on the concentration against T, and if that is linear and has a positive slope, you've got a second order process. Once you've identified whether it's zero, first order, or second order, what you want to do is look at your slope, because that's going to give you your rate constant. Now, you can do all of this, all three of those plots, and calculate all three of those slopes in your calculator fairly quickly using what's called a stat table. And I published a video in the resources that shows you how to do that. So if you've got a Texas calculator and you'd like to do that, one of those TI calculators, then I would suggest checking that out. There are other ways of kind of making these calculations a little arduous, sort of by hand, and I've got a second video that shows you how to do that. The preference is, though, if you can figure out how to use the stat table, that's really going to help you a lot. Now, for each of these forms of reaction, zero order, first order, and second order, there is a corresponding half-life expression. And sometimes this can also be helpful in figuring out the order of a reaction, because the half-life for a first order reaction is not dependent on the concentration and doesn't change as the reaction progresses. For a zero order reaction, the half-life is dependent on the concentration of the reactants, and it actually decreases as the reaction progresses. And for a second order process, we will find that the half-life of our reaction increases as the reaction progresses. So that can be helpful sometimes. If you have the right set of data, you can actually eyeball whether it is zero, first order, or second order.